Alrighty, lads and ladies, welcome back to Calc 2. I'm glad to see everybody here. Today we're going to continue talking about infinite series. We've got some really cool shit to discuss, and I'm excited to share it with you. So I think last time we talked about the integral test, and we were able to work a handful of examples. There's one or two more examples I wanted to look at with the integral test before we move on to section 11.4, which is the next section. That's all about comparison. Like I said, before we get to the comparisons, I want to talk a little bit more about the integrals. So let's do it. Give me just 1 second to get everything switched over. I'll have to replenish my coffee soon, but I'll wait for a little writing break to do. Okay. There we go. I apologize for the fan noise. My office hour recorder. That's an office hour. We don't need to convert that. It'll be showed up anyway. All right, stop converting. I also apologize for the cat noises outside. There's a neighborhood stray that we've been kind to who is just sitting at my front door meowing nonstop. So hopefully he gives up on that soon. This, of course, is MAC2312, section 004. It is a lecture. And today is the 18th of March, 2021. It occurred to me that we missed Pi Day, and that was a sad thing. So happy late Pi Day, if I didn't say that on Tuesday. Today, we're going to do a little more with the integral test. And this was section 11.3. The main lecture on that was the last one. And then we're also going to talk about comparison tests. This is section 11.4. Of course, all of this is stuff for infinite series. So you should now be fleshing out your page on convergence tests for infinite series. We have a handful of results though, and however you want to organize them is up to you. But just be mindful that today we were talking about series. Tuesday we talked about series. All of the stuff we've been doing lately is related to infinite series, not sequences. And it's very, very important you keep clear in your head the difference between a sequence and a series. All right. There's just one example with the integral test that I wanted to play with that we didn't get to do last time. So I'm going to begin with that. Actually, before I get in there, let me some comments on the integral test. No. All right. Showing, so remember, we need to show, to use the integral test, which I'll abbreviate as IT, to relate the series sigma an to an integral f of x dx. And the series is summed usually from, I'll say a to infinity, integral a to infinity, where f of n is equal to a sub n, right? So, you know, to relate the series to the obvious related integral, we had to show, or one must show, that f of x is positive, i.e. that f of x is greater than or equal to 0 for all x in the interval a to infinity. This is not any real work, right? You just have to show that your function is not negative, meaning you have to verify that this inequality is true everywhere on this interval. You have to show that it's continuous for all x in the interval a to infinity. And when it comes to showing that a function is continuous, the best way to do this identify anywhere the function is discontinuous and then state that those x values are outside the interval a to infinity. To this end, the theorems of section 2.5 are useful. So I don't know how well everybody's Calc 1 class covered Chapter 2. I think I mentioned in passing the other day that my wife's Calc 1 class skipped over that shit entirely, and I don't fault you for that. If your class did not cover this stuff well, that's not your fault. However, you are now responsible for it. This is the nature of the beast. You have progressed on to Calc 2, and thus I am allowed and indeed need to assume that you know the material from Calc 1. So if there's a gap in your knowledge here, don't be shy about it. Come back in the textbook to Chapter 2, Section 5, and read the thing. It's a good book, right? It's a genuinely good book. Read the words, study the graphs, work the examples, and make sure you understand. And I am more than happy to spend time with you in office hours going over this, not only because it's good for us, but you come to my office hours and ask questions about 2.5, then my Calc 1 students who are in there also get the opportunity to review that. It's a teachable moment on like 4 or 5 different levels, and I enjoy it genuinely. It's beautiful stuff, happy to do it, and it will help. The main useful theorems here are that polynomials are continuous everywhere, rational functions are continuous everywhere except for the bottom is 0. And then this theorem down here, the following functions are continuous everywhere in their domain. These are nice. And composites of continuous functions are continuous. So you mash together continuous functions, the result will be continuous, but you need to know these theorems. So if they're not familiar to you because your Calc 1 teacher thought that shit wasn't important, your Calc 1 teacher was wrong. And we need to go back and make sure that we're comfy with those. The other thing I wanted to share with you, I guess 2 other things I want to share with you. Of course, the third thing we need to do, aside from positivity and continuity, we need to show that the function is decreasing. And the truth is that it doesn't need to be decreasing everywhere on the interval a to infinity. It needs to be decreasing on some interval of the form, let's say, c to infinity, where c is greater than or equal to a. In other words, the function needs to be eventually decreasing.
Can I ask a question?
Sure.
These all have to be true, right? We can't just pick and choose one.
Correct. All 3 must be true. In order for the series and the integral to share convergence, which is what we want when we use the integral test, all 3 of these must be true. So if your function isn't positive, but it is decreasing and continuous, then integral test doesn't work. If your function is positive and continuous, but it isn't decreasing, the integral test doesn't work. So yeah, we need to verify all 3 of these things. And then kind of what I was excited to share with you guys today are mostly to do with the decreasing thing. So the fact that you don't actually need to be decreasing everywhere on the interval a to infinity, just eventually decreasing, that's what this means, right? So from somewhere to infinity, the function needs to be decreasing. It's allowed to wobble a little bit at first, but then at some point it needs to start decreasing and it needs to continue to decrease from that point on. So as long as your function is eventually decreasing, meaning from some point on it is decreasing, even if that point isn't the first point in the interval, that's okay. And then the other thing that I wanted to talk about with relation to decreasing are kind of the tricks that are useful for showing decreasingness. To this end, we can use the following arguments. The classic is f primed of x is less than 0, right? If the derivative is less than 0 for all x in a to infinity, or eventually, right? Even if this isn't true, like if you're looking from 1 to infinity, but your function starts decreasing at 5 and it's decreasing from 5 to infinity, that's okay. That works. So the classic is just show the derivative is negative. But sometimes solving an inequality like this is hard work, and we'll see examples where that can be a little bit tricky. In fact, one of the examples from Tuesday, that was a little bit tricky, right? We had that function that was decreasing from 1 over the square root of 2 onward, and it took a meaningful amount of computation to get that information out. So other ways that we can get at this, observe that f of x is the reciprocal of an increasing function. That is, it's equal to 1 over g of x, where g of x is increasing. And this is often faster, right? So there are a lot of functions whose graphs we just know. And if the function you're messing with, f of x, is the reciprocal of one of those whose graph we know, and hence can just say, yes, I know this is increasing, then the reciprocal of an increasing function is automatically decreasing. So this is because the reciprocal of an increasing function is automatically, what a great word, decreasing. There might not be two L's in automatically, I'm not sure. So that the derivative, take the derivative, show the derivative is negative, that works often. But sometimes it's more time consuming than the latter. So like 1 over e to the x or 1 over x to some power, those are all reciprocals of obviously increasing functions. And you can make that argument. Just make sure if you're going to use the second point there that it's actually the case. Don't try to tell me that like x over ln x is decreasing because it's the reciprocal of an increasing function. It's not. That sort of shit. Okay. I guess another little comment here, the eventually thing, that actually holds for a lot of what we're going to do with series. It's not necessarily the case that that all the hypotheses of these theorems are as thin as they can possibly be. A lot of the convergence tests have statements like if da 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 is true, then da 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 is true. And sometimes you can relax a few of the things that come after the if and still get a true statement. So I'll be mindful of those things and I'll mention them as we run into them. And you are free to use those things. So if I tell you you can relax this hypothesis from for all x to for all x sufficiently large or something like that, then you're free to use those versions of the theorems on exams. Just make sure if you're going to try to do that, that you do it carefully. Don't get sloppy. The Discord for this class has been very, very quiet lately, and I would like it if that was not the case. I would like to see you guys sharing your solutions more with each other there. Again, I want to encourage you to please check your logic by bouncing it off other people. That shit matters. It really does, because you don't want to come into exam 2 here thinking that you're a master of convergence tests only to discover that that's not the case. So please make sure you're bouncing your solutions off of other people, having them check your logic, check your grammar, things like that, because there's a lot of writing here. Okay. So the example I wanted to look at with you guys was one of the examples I wanted to look at with you guys was to investigate the convergence of the series S equals sigma n from 2 to infinity 1 over n times the natural log of n. Just to make sure we're on the right page, S here would be 1 over 2 times ln2 plus 1 over 3 times ln3 plus 1 over 4 times ln4, and so on. The series has to start at 2 because the natural log of 1 is 0, and that would give us a 0 downstairs. So the first term of the sum wouldn't be defined, and that wouldn't mean the whole series converges. It just means that the series isn't well defined. You cannot talk about that series. If you ever see something like that, that means there's a typo. All right. So these are what the first few terms of the series look like. Is this geometric?
No.
No, it's not, right? Definitely, you can't multiply by some fixed constant to go from here to here or here to here. It's not geometric. It's not telescoping. It's not any of that shit. So the integral test is our only real tool. You could have tried using the test for obvious divergence, but of course it's going to pass that, right? As n goes to infinity, the downstairs here goes to infinity. So this thing would, the general term would go to 0. So the only thing that's worth trying here is the integral test. And remember, we always let our reader know what test we're doing. Always tell the person who's reading your paper what the fuck it is that's going on. So don't start without saying, oh, I'm doing the integral test, or I'm doing TFOD, or I'm doing this or that. Make sure you write that down. The corresponding function here, f of x, is 1 over x times the natural log of x. And we need to show that this function is positive, continuous, and decreasing. So is this positive? Well, 1 over x times the natural log of x will be greater than or equal to 0 as long as x times the natural log of x is greater than 0. Right? The bottom can't be equal to 0. And 1 over something is positive as long as the something down there is positive. When is this true? Well, this is certainly true if both x and the natural log of x are positive. X is positive when x is greater than 0. And ln x is positive when x is greater than 1. So it's not the only way for this to be positive. They could also both be negative, but I'm not interested in that shit because I'm interested in x's running from 2 to infinity. So I'm just sort of verifying that, yeah, this function is positive on the interval 2 to infinity. So therefore, f of x is greater than or equal to 0 everywhere on the interval 2 to infinity, which is what I need, right? It's actually positive on a much larger interval, but 2 to infinity is what I need. Is this function continuous?
Yes.
Well, yes, but not everywhere. So remember, the idea here is I want you to tell me where the function is discontinuous and then verify that those numbers are not in the interval in question. So
It's not defined at 0.
good, where else?
Oh, at 1,
Good.
which are both less than 2. So in our interval, it's continuous everywhere.
Good. That's exactly the way we want to phrase this. So f of x is undefined / discontinuous at x equals 0 and x equals 1, neither of which lie in the interval 2 to infinity. So we're good. This is kind of the simplest way to convince me that you know what you're talking about. That's what I'm trying to model here. All right, what's the simplest way to convince me that you actually know this thing is continuous rather than just saying it is? Tell me where it's discontinuous. Tell me where it's discontinuous and then just make a comment that this thing ain't in the interval in question, so we kosher. All right. What's the easiest way to argue that this is decreasing?
And its derivative.
We could
Can we do 1 over this so we'd have just actual mass instead of trying to deal with?
Yeah, very good. So I would say here we can use that reciprocal argument. F of x equals 1 over x ln x is the reciprocal of x ln x. Since both x and ln x are increasing functions, and the product of 2 increasing functions is increasing, f of x is the reciprocal of an increasing function. Right? That's the clean way to argue this, I think. You could also take the derivative. All right, you could take the derivative here. It's going to be a little bit complicated. I would advise that you do it using the chain rule, chain and product rules, and then solve the inequality f of x is less than 0. Right? You make your number line for f primed. F primed of x is less than 0. You make your number line for f primed, plot your critical numbers, test points, and find for me exactly what intervals f is increasing and decreasing on. But here I can just say quickly that this bottom, I think that's an increasing function. Why do I think that's increasing? Because f of x, like x on its own, is an increasing function. I know that graph. Natural log of x on its own is an increasing function. I know that graph. And if you multiply 2 increasing functions, you get an increasing function. Therefore, this is 1 over an increasing function, i.e. it's the reciprocal of an increasing function, and we know that those are always decreasing. So this is as quickly as we can get through these 3 hypotheses, and you notice it is still quite a bit of work. All right, now I can compute the integral. The integral from 2 to infinity, 1 over x times the natural log of x dx. You need to do these carefully. You need to write them as limits and treat it all formally. This is lim r to infinity, integral 2 to r, 1 over x times the natural log of x dx. How do we do this improper integral?
U sub
Very good.
u is equal to ln x, which means du is equal to 1 over x dx.
Excellent. Thank you, Cody. It's Cody, right? Oh, yeah, thank you, Cody. Excellent. And while I'm here, I'm going to change my bounds. My old lower bound was 2. My old upper bound was r. When x is 2, u is the natural log of 2. When x is r, u is the natural log of r. So my new integral, I will have lim r to infinity integral natural log of 2 up to the natural log of r 1 over u du. Right, this 1 over x here is getting soaked up by my du. Sorry, 1 over x here. This piece, the 1 over x, is du. So he goes away. And now this is not a difficult thing to compute. This would be lim r to infinity natural log absolute value of u from ln2 up to ln r. And I suppose I'll continue this down here. Gives me lim r to infinity. And then this is kind of cute. I'll have the log of r minus the log of 2. This reminds me of a great joke. You're going to hate this. What sound does a drowning analytic number theorist make? Log, 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 log. It's bad. It's real bad. But this sort of thing, logs of logs of logs of logs, they show up a lot in certain places, particularly analytic number theory. Anyway, as r goes to infinity, we need to sort out this piece. This piece is clearly finite, right? The natural log of 2 is somewhere around 1/2. So the natural log of 2 is like negative natural log of 1/2 or something like that. So, but here is what I need to figure out. So as r gets bigger and bigger and bigger, what does this piece do? What are you guys thinking?
Well, natural log of a really big number is a really big number.
Good.
So we'd have natural log of infinity again, which is just a really big number again. So it's divergent.
Good. Very good. That's perfect. Everybody hear what Cody said? The
Alexander, not Cody.
Oh, I'm so sorry, Alexander. I'm sorry. So what Alexander said is that the inside piece here, the natural log of r, as r goes to infinity, this whole piece inside here goes to infinity. It does it very slowly. The natural log of r very slowly goes to infinity, but it does go to infinity. So this thing is like the natural log of infinity. And that goes to infinity. So this is like ln of infinity minus ln of 2. And since the ln of infinity is infinity, this is infinity. And now we can finish things up and say, therefore, integral 2 to infinity 1 over x ln x dx diverges. So by the integral test, the series S diverges also.
If we had gotten a value instead of having an infinity here, would that be what the whole series converged to, or just the fact that it converged?
It's not, and this is something I mentioned in our class on Tuesday. The integral and the series are not equal to each other. So just because this integral comes out finite doesn't mean that that finite value is equal to the series. It just means that the series is also finite. So like if the integral comes out to 5, does that mean the series is equal to 5? No, not necessarily, because the area under the curve isn't the same as the area in the rectangles. Remember that kind of analogy from Tuesday?
Yeah.
So there is a relationship between them, and the textbook does explore that relationship in some depth. And if we had, an extra week or two for this class, I would absolutely be having you guys go through this theorem on estimation using the integral test. But it's not true that the series and integral are equal to each other. There is a concrete relationship between them. This inequality describes the concrete relationship between the integral and the series, but they're not equal. So for us, all we say is that if one is finite, so is the other. I want you guys to look this over. Let me know if you have any questions. I need to use the bathroom. Refill the coffee too. Let's do that. Okay. Any questions on this? The structure of the argument is important, not just the calculation. I want to say that. This last bit, this is the important part. We got to go through the hypotheses of the theorem and make sure that they're satisfied, and we have to conclude appropriately. So pay attention to the language that I use, especially in these last little bits. And again, try to mimic them in your solutions. You don't have to use precisely this language. I would encourage you to use your own flavor of this language. But make sure you're using the words right, make sure you're speaking in proper grammar, and make sure that your answer is actually answering the question. Remember what we asked is, does the series converge or diverge, right? What's the convergence result for the series? So at some point, you got to tell me whether the series converges. Don't just tell me the integral diverges. All right. Do you guys remember the comparison theorem for improper integrals? For type 1 improper integrals, we know that if f of x is less than or equal to 0 is less than or equal to f of x is less than or equal to g of x for all x in the interval a to infinity, then if the integral from a to infinity of f of x dx diverges, that implies that the integral from a to infinity of g of x diverges. Oh, sorry, there should be a dx here. Shit. Dx diverges. And if the integral from a to infinity of g of x dx converges, that implies that the integral from a to infinity of f of x dx converges. It was a containment argument, right? We said if this inequality is true, then the area under f has to be smaller than the area under g. So if the small area is infinite, then the large area has to be infinite. And if the large area is finite, then the small area has to be finite. The analogous result for series is also true. So it's time for a theorem. And this is called the direct comparison test. It's the first theorem in section 11.4. And it's the last theorem on your homework for this week. So I'm only covering half of 11.4 this week. I want to go slow and make sure you guys have time to practice things. There's 2 comparison tests for series. That's why I'm specifying here. This is what's called the direct comparison test. The other one is called the limit comparison test. And we're going to talk about that next Tuesday. So don't just remember this as the comparison test. It's a comparison test. Which one? The direct comparison test. This says if 0 is less than or equal to an is less than or equal to bn for all n, then sigma n from wherever to infinity an diverges implies sigma from n equals wherever to infinity of bn diverges. And if sigma from n from wherever to infinity bn converges, that implies that sigma from n equals a to wherever of an converges. So these are 2 very similar theorems. And that's the analogy with improper integrals coming through again, right? Just like it did for the integral test. Since there is a way to compare integrals, there is a way to compare series. This is your next convergence theorem for infinite series. And it's probably the most useful one. It's not the most powerful in the sense that there's plenty of things where it's kind of hard to use this, but it's the most useful in that it's the kind of easiest to understand. If you're smaller than something finite, you got to be finite. If you're bigger than something infinite, you got to be infinite. So let me show you how this works. Let's look at a few examples. I told you that anytime you can relax the hypotheses of a theorem and it still remains true, that I would let you know. Here it is. you can replace for all n with for all n sufficiently large. That inequality doesn't need to always be true. It just needs to be true eventually. What I mean by eventually is, as n gets bigger and bigger and bigger, if this inequality isn't true for n equals 0, 1, 2, 3, 4, 5, that's okay, as long as it is true from 6 to infinity.
Is that 6 chosen arbitrarily?
Ask the question one more time. I didn't quite hear you.
Is that 6 chosen arbitrarily, or is that like a specific value you're looking for, or what do you mean by?
Oh no, yeah. 6. I just made something up. Yeah. There's nothing special about 6 there. It could be 10, it could be a million, as long as for some point onward, this inequality holds. As long
Even
as
if
that's true.
Even if that some point onward is inside of our interval.
Yeah, as it could be, as long as this inequality is true from n equals 10 billion to infinity. I don't care about the first 999,999,999 terms. I really only care about the infinite string of terms that comes at the end. Those are the ones that determine whether the series converges or not. In other words, the convergence of a series really doesn't care about the first finitely many terms, even if that's a large finitely many. The first 10 billion terms of your series could be very, very big. But as long as the infinitely many terms that come after that converge, you'll get a convergent series. So only the tail matters, in other words. All right. Example.
How do we show that that's true?
Well, so just like the big deal in using the comparison test for type 1 improper integrals was building the inequality, here the big deal will again be building this inequality. So let me show you through an example, and I think you'll get an idea. But basically, we start just like with the squeeze theorem or with the other theorem for integrals. You start by constructing this inequality, and then you make an observation about one of the two and deduce something about the other. So I think examples are our friend here. Investigate the convergence of the series S equals sigma k from 2 to infinity k over the natural log of k. Do we want to do this? No, actually, sorry. Let me alter this. I don't want to start with something too confusing. Let's start with sigma n from 1 to infinity. Natural log of n over n. Yeah, this will be easier. So I want to know, does this series converge or diverge? Just so we're clear what the series looks like, this is ln1 over 1 plus ln2 over 2 plus ln3 over 3 plus ln4 over 4, and so on. Writing out the first few terms of the series, always a good idea. Before we even get started, I would like to hear your thoughts. Do you think this series converges or diverges, and why?
I think it passes the test for obvious convergence.
It does. Yep, it'll get through that. We can run that. We haven't done one of those in a little bit, so I'll actually run that test just for gits and shiggles. Yeah, Matthew, you're correct. So let's look at the test for obvious divergence just real quick. Remind me what that says. What does TFOD say? I forget. Anybody? feel free to look back in your notes. Will make me a sad panda. So someone said that this series passes this test. That person is correct. What does the test say?
If it's greater than 0 for all sufficiently large n, then the direct comparison test may apply.
So that's direct comparison, but that's not related to this. Matthew, you're closer. So Matthew sent me, if the limit of an is equal to 0, then the series is convergent. That's not true, but it is a common misunderstanding about TFOD. So let me real quick, let's remind ourselves what this says. This says, if the limit as n goes to infinity of an is not 0, then sigma n from wherever to infinity of an diverges. And it's an important thing that we say, if the limit as n goes to infinity of an is 0, the test is inconclusive. So I'm not picking on you when I say this, Matthew, that the bottom thing is a common misunderstanding. That's why I insert the O here, obvious divergence. If the limit of the ANs is not 0, then this motherfucker has no chance. You're adding up a bunch of big shit. You're gonna get big shit. And if the limit, that's okay, don't feel bad, don't feel bad. It's literally a true-false question that shows up on at least one of my tests every semester, either exam 2 or the final. It's a very, very common misconception, and I would rather us make it here and get it out of the way. If the limit of the ANs is non-zero, then the series sigma AN automatically diverges. If the limit of the ANs is 0, then we don't learn anything. It could go either way. Remember, kind of the intuition here is that for the series to converge, we need the ANs to go to 0 fast. Not just to go to 0, but to go to 0 fast. So going to 0 is a prerequisite for even having a chance. Think of, I don't know, obviously, but yeah, going to 0 is necessary for the series to converge. It's not sufficient though. So let's try running this test on this particular series.
Both top and bottom go to infinity, but bottom goes a lot faster than top does.
Correct. So if I run TFOD here, it's good to get practice with this though. Here, the limit of the ANs is the limit as n goes to infinity of the natural log of n divided by n itself. Alexander is correct in saying both the top and bottom are going to infinity, and he's also correct in saying that the bottom goes to infinity faster. How do I make that quantitative and actually use it to prove that this limit is 0?
L'Hopital's.
Very good, L'Hopital's rule. So since the top and bottom both go to infinity, I can apply L'Hopital's rule. I get 1 over n as the derivative of the top and 1 as the derivative of the bottom. And this now goes to 0 over 1, which is just 0. So TFOD is inconclusive. Sadly. If the limit comes out to anything other than 0, either it doesn't exist or it comes out to some non-zero number, then we could say the series diverges right away. If the limit does come out to 0, we don't learn anything, sadly. Remember sigma 1 over n, the harmonic series. That's a divergent series, but the ANs there do have limit 0. And in fact, that's going to be a useful result for us here. All right, so TFOD, no dice. Got to try something else. We could use the integral test here, but it's a pain in the fucking ass. I don't want to do that. I don't think you do either. I don't want to spend a whole page writing out positive and decreasing. What's worse is that the function here, it's not at all obvious that this thing is decreasing. It is eventually decreasing. I think it starts decreasing at like 1 over e or something, or maybe e itself, but it's not at all obvious, and it's going to be quite a bit of work involving derivatives to show it. So I would rather use a comparison test. So I'm going to tell my reader that my next move is a direct comparison test because PFOD was inconclusive. Now, the first step in using our comparison test is to construct an inequality. Right? This says if you have an inequality of this form, then you can make conclusions like these. So it's up to us to build this inequality. And how you choose to build the inequality will depend on whether you think the series is convergent or divergent. If you think that this series is convergent, then I should try to find something a little bit bigger than this guy whose convergence is easier to work out. If, on the other hand, you think this series is divergent, then you should try to find something a little bit smaller than this guy whose divergence is easy to work out. In other words, I'm trying to figure out, do I think of this as an, or do I think of this as bn? If I think this series is convergent, then I'm going to think of ln of n over n as the middle guy here and try to squish him underneath something bigger whose convergence is known. Because then I can say, okay, big guy converges, therefore small guy converges. If, on the other hand, I think that this series diverges, then I'm going to be thinking of ln n over n as the bn's. And I'm going to try to slide something smaller underneath him whose divergence is easy to show. And then I can conclude that my guy diverges. Very good, Matthew. Yeah. The thing against which we will compare here is the harmonic series. So I have to construct the inequality. 0 is less than or equal to, let me say it differently here. 0 is less than or equal to 1 is less than or equal to the natural log of n. Now this isn't always true, is it? For instance, the natural log of 1 is 0. That's not bigger than 1. The natural log of 2 is like 0.6, which is also not bigger than 1. This is true for all n greater than or equal to 3. Remember, we're thinking of n as being integers. The natural log first becomes larger than 1 at e. E is like 2.7. So this part of the inequality is only true if n is bigger than e. And so since we're talking about integers, that means n has to be at least 3. From this, we can deduce that 0 is less than or equal to 1 over n is less than or equal to the natural log of n over n. Again, for all n greater than or equal to 3. And this is where the sufficiently large thing is useful, right? Here, sufficiently large happens to be 3. This inequality isn't true if n is equal to 1 or 2, but it is true for 3, 4, 5, 6, 7, 8, all the way off to infinity. And that's good enough. Now, since we know that sigma n from 1 to infinity, 1 over n diverges by the inequality above, and the direct comparison test our series S equals sigma n from 1 to infinity natural log of n over n must also diverge. And this is how a nice clean DCT problem goes. So just like with the comparison test for improper integrals, just like with the squeeze theorem, you have to start with an inequality that you know is true and then build up the inequality that you need using algebra. So the labels actually don't matter. Matthew makes an interesting point here. What's the difference between AN and BN? In this theorem, BN is just the larger term. Right, so in the statement of the theorem here, there's no convenient way to do this. In the statement of the theorem here, BN is just the larger term. I have to give them names in order to write this down. But don't worry about who is AN and who is BN. Just worry about the positions in the inequality. So if the big guy converges, the small guy converges. And if the small guy diverges, then the big guy diverges. Right? Since I know the series sigma 1 over n diverges, and 1 over n is smaller than natural log of n over n, I know that the series sigma natural log of n over n must also diverge, because term for term, it's larger than the natural log of n over, or term for term, natural log of n over n is larger than 1 over n. Yeah, so back here in the inequality, technically this would be our AN, and technically this would be our BN, but it really doesn't matter. The labels make no difference and have no bearing on the function or utility of the theorem.
How did you choose 1 over n here?
That's the big question. Few things. First, this observation is fairly easy to jump to, right? I know that the natural log function gets big. It gets big slowly, but it gets big. So certainly it's larger than 1. But really what's going on in my mind that leads me down this path is when I look at sigma natural log n over n, when I look at this series, I'm seeing, I write out the first few terms and I recognize that the denominator is the same as the 1 over n denominator, which I know is divergent. And I recognize that the tops, at least most of them, all the ones that come after here, are bigger than 1. Oh, that's cool. I never realized this had a button for that. So how did I come up with the 1 over n? Well, I see that there's a 1 over n hiding in here. And I see that the top is bigger than 1. Not right away, but most of the time. That's what tells me to compare against 1 over n. So usually, and this is true in general, as you're trying to pick things to compare against, you want to try to suss out sort of the word is asymptotic. You want to suss out the asymptotic behavior of your function. Natural log of n grows and it grows to infinity, but it does it very, very, very slowly. So the dominant term in this expression is the 1 over n. That's the most powerful thing going on here. Like, remember when we did TFOD, we said, okay, well, they both go to infinity, but n goes to infinity way faster. So n is the dominant term, which means 1 over n is really the major behavior of this series. And that's what tells me to compare against 1 over n. Does that make sense? Matthew, have I answered your question about the labels and the inequality? I know that this can feel a little bit strange, just like using labels and then saying they don't matter. Are you comfortable with that? Okay. Okay, cool. Yeah, so the big thing is to build an inequality where the far left side is 0 and one of the other guys is the thing in your series. If you think that your series diverges, you should try to make the thing in your series show up on the right. If you think your series converges, you should try to make your thing show up in the middle. And the left side always has to be 0. The reason for this is if some of the terms are negative, that throws all of this shit out of whack. All the convergence tests we have at first will only work for series with positive terms. Okay, let's look at some more DCT examples. How am I doing on time? We're doing okay. 1:32. Yeah, we're good. So, oh yeah, duh. All right, let's investigate the convergence of the series sigma n from 0 to infinity 1 over 2 to the n plus 1. Again, always wise to write out the first few terms of the series. S is equal to, I'll write it in sigma notation first.
Is that 1 plus 2 to the n, or is that 2 to the parentheses n plus 1?
The plus 1 is not in the power. Yeah, so it's 1
Okay.
plus 2 to the n. So this would be 1 over 2 to the 0 plus 1 plus 1 over 2 to the 1 plus 1 plus 1 over 2 to the 2 plus 1 and so on. So that's 1/2 plus 1/3 plus 1/5 and so on. Is this a geometric series?
No.
No, it's not. It may look a little bit like one, right? 1 over 2 to the n on its own is geometric. And Alexander, if that plus 1 was in the power, then it would be geometric as well. But writing it out like this, we see pretty easily that this is not a geometric series. To go from 1/2 to 1/3, you would have to multiply by a different constant than to go from 1/3 to 1/5. So right away we see, nope, it's not geometric, even if it kind of looks similar to one. But that similarity gives us a hint. It does look similar to a geometric series.
We could compare it to a true geometric series, 1 over 2n, since it's less than, or it's greater than 1 over 2n plus 1. So if it converges, then we know this must converge as well.
Perfect. So let's say it carefully and let's talk about how to build that inequality. I would start by saying, well, let's see. It's so kind of obvious here that I don't know how to build it up without.
Actually, wouldn't this be a p-series, not a geometric series? Sorry.
No, not a p-series. Not a p-series. P-series is 1 over n raised to a constant power. So I would say here that 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n. And both of those things are positive. How do I know this? Well, because the denominator is bigger. Bigger denominator means smaller overall. That's how I get this. And of course, exponentials are always positive. 2 to the n is always positive. You add 1 to a positive thing, it stays positive. So the reciprocal of a positive thing is positive. So this end of the inequality is fairly obvious. This end of the inequality comes from the fact that a larger denominator makes you smaller overall. This is true for all n, right? This would be true regardless of n, as long as n is positive. Also, sigma n from 0 to infinity 1 over 2 to the n. This is sigma n from 0 to infinity 1/2 to the n. The algebra there is just that 1 to the n is 1. So this is like 1 to the n over 2 to the n, which is the same as 1/2 to the n.
Wait, if n was negative, would this not be true?
I'd have to think about that for a second. That's why I hesitated there.
I think it's just true everywhere.
It might be true for all n, but in particular, I need to make sure that it's true here. All right, this is my interval of question, and it certainly is true there. But yeah, it may be true everywhere as well. I don't see any reason why it would not be.
Because 2 to a power can't ever be negative.
Yeah, I'm not
And
worried about this side breaking. I'm worried about this side potentially breaking if n is negative, but it shouldn't. I think it's true for all real numbers n, in fact. But regardless, it's definitely true where we care about. And then this fella, which is the sum of the thing on the right, is equal to this fella, just because 1/2 to the n is the same as 1/2 to the n. And this is a geometric series. With r equal to 1/2. So the absolute value of r is the absolute value of 1/2, which is 1/2, which is less than 1. So sigma n from 0 to infinity, 1/2 to the n converges. Am I done? Not yet.
no, we have to state that the original function converges, the original series converges because of the DCT test.
Very good. So remember, we have to make sure we're answering the question asked. It's true that 1/2 to the n summed from 0 to infinity is a convergent geometric series, but that's not what we were asked about. We were asked about this guy. So we'll say, therefore, by the inequality above and the direct comparison test, sigma n from 0 to infinity, 1/2 to the n plus 1 converges also. So that last line is important. And again, pay attention to the grammar, pay attention to the use of words, notation, all of it really does matter. Are there any questions on this one? Okay, I think I'll take one more question here as an example, and then we'll take a little break. And then we'll come back and solve a few other problems for with lab. Yeah, this could be fun. Let's do it. Let's do it like this. Just making shit up, really. When I look at this series, if all I'm thinking about is convergence, I don't care about the value of the series. What I see is that upstairs, I have a linear function of n. I have a degree 1 polynomial. And that downstairs, I have a cubic function of n, a degree 3 polynomial. So the asymptotic behavior here is basically n over n cubed, or 1/n squared. Now, if I want to make, so that makes me think it converges, right? Because sigma 1/n squared is a convergent p-series. if I want to be concrete about this, then here's what I do. I would begin by saying something like 1 over 5n cubed plus n squared plus 3 is definitely less than, you could say less than or equal to 1 over 5n cubed. The other things that are added here are positive. So you make a bigger denominator, the whole thing gets smaller overall. And this is greater than or equal to 0. Again, this would be true for all n, regardless of whether it's positive or negative, but we'll say specifically for all n greater than or equal to 1. Therefore, if I multiply through by 2n, I get 0 is less than or equal to 2n over 5n cubed plus n squared plus 3 is less than or equal to 2n over 5n cubed. Now, the series sigma n from 1 to infinity 2n over 5n cubed is equal to, just doing some algebra, sigma 1 to infinity 2 over 5n squared, which is equal to 2/5 times sigma n from 1 to infinity 1 over n squared. Is a multiple, it's a constant multiple of a p-series. And that p-series has p equal to 2, which is bigger than 1. So sigma n from 1 to infinity 2n over 5n cubed converges. Thus, by the inequality, and since I have multiple inequalities here, it's nice to say which one. Thus, by the inequality star, and direct comparison test, the series S converges also. And you see kind of why I like naming the series, so I can refer back to it later without having to write the whole thing. Just saves, you know, I get these calluses on your hands from writing too much. Can help with that a little. So this is the direct comparison test. The particular examples that we've looked at so far are relatively simple, as they should be, because you're just now meeting this thing. But they can get quite complicated, and it really all comes down to your skills with the inequalities. So we want to build up these skills. We want to have been working on this back, of course, in section 7.8 and previously when you learned about the squeeze theorem in Calc 1. Hopefully those skills are there, but if they're not sharp yet, you need to continue to refine them and make that a goal. That's a big goal for 11.4. The other big goal for 11.4 is the other comparison test, which is called the limit comparison test. Now, I'm not going to drop that on you this week. At least I'm not giving you any homework problems with it, but I may kind of introduce it to you a little bit in lab today. but I don't want to overwhelm. So we can take a quick break here. I think we are at the proper break point. We'll come back at 2 o'clock and we can work whatever sort of problems you guys want to look at. I'm not going to push you too hard today. I just want to make sure that you're comfortable and you feel like you can solve the problems you need. So we're going to take a little break and we'll come back in about 15 minutes. All right?
When we come back, will you be taking homework questions?
Yes. Yep.
Thank you.
All righty. I'll see you guys in a few minutes. Hey guys, I'll be back. We'll be getting started here in just a few minutes. I got a bit distracted making my lunch, but give me like 3 more minutes. We'll be back rocking and rolling. Alrighty, guys, we're back, and I am ready to take homework questions, whatever you guys would like to work on for the next hour or so. So any particular problems you want to see from the last few homework sites, I'm happy to talk about.
I have one.
Okay, what would we like to do?
Homework 9, question 6.
Alrighty, and while I'm waiting for this to load, if anybody else has homework problems they want to look at, you can go ahead and type them into the chat there, and we'll go through them in the order that they arrive in chat. So let's see, homework 9, problem 6. Yeah, this is fun. So we did something similar to this in class the other day. What we want to do is investigate the convergence of the sum. So starting at 1. Yeah. Square root of n plus 7 over n squared. And the problem has a few little details to it. They ask us to say that this can be split up into two series, which are p series, and then give the value of p for each one of them, right? So they say the series is equivalent to the sum of two p series. Find the value of p for each of those. So first, in order to split this up, we need to do a little bit of algebra, right? What's my first step going to look like here?
Split the denominator and the numerator into separate guys.
Something like that. It's not like I can say sigma the top minus sigma the bottom or anything, but the algebra here looks like this. This is root n over n squared plus 7 over n squared. Right? Fractions, this is how they add, yeah? And now I can split up that series as sigma n from 1 to infinity, root n over n squared plus sigma n from 1 to infinity, 7 over n squared. And this will get us closer to seeing how we can understand this as a sum of two p series. This plus right here is what they mean by a sum of two p series. So each of these, if we use a little lecture logic, we can deduce should be able to be rewritten as p series. The second one I think is a little bit easier. You see right away that you can pop out that 7. So if I come down to my next line here, I see that this guy can be written as 7 times sigma n from 1 to infinity, 1 over n squared. The first guy just requires a little bit more rules for exponents. Remember, if you have like x to the a over x to the b, that's the same as x to the a minus b, which is the same as 1 over x to the b minus a. Bunch of different ways to do it. Here, the 2 downstairs, there's more n's downstairs than there are upstairs, right? This is like n to the 1/2 divided by n to the 2. So if you simplify that, you can write it as sigma n from 1 to infinity, 1 over n to the 3/2. Right? Because 2 minus 1/2 is 3/2. So a kind of rule that we're using, the algebra rule that we're using there is this one. And each of these are p series. If we're careful, this one is actually a multiple of a p series, right? But the series in question here are p series. This guy has p equal to 3/2, which is bigger than 1. So this is convergent. This series converges. And this fellow has p equal to 2, which is also bigger than 1. So this series converges. And then I would say, since the sum of two convergent series is convergent, the original series must converge. Any questions on these steps or any one of these pieces?
No, that looks good.
Alrighty. Moving along. The next one was homework 8, number 29. So this is actually homework 9, right? So while I've got homework 9 up, let me return to problem 1, which was Lydia's question, and then we'll take a look at homework 829 from Alexandra. I know it's going out of order, but I can be patient. They tell us to use the integral test to determine whether this series is convergent or divergent. And Lydia was specifically curious about how to show that this thing, the function in question here, satisfies the criterion. All right, investigate convergence of s equals, we started at 1 or at 0, sigma n equals 1 to infinity n over n squared plus 9 using the integral. So indeed here we need to check and see that this satisfies the hypotheses of the integral test. The function f of x here is going to be x over x squared plus 9. And in order to show that this is decreasing, we have to use the derivative because this is not the reciprocal of an obviously increasing function. If it was 1 over x squared plus 9, then I could say that, but it's not the reciprocal of an increasing function, so at least not in any obvious way. So I would say first, is this positive? Well, yeah, f of x is greater than or equal to 0 if and only if x over x squared plus 9 is greater than or equal to 0. And this is true if and only if x is greater than 0, because the bottom, x squared plus 9, is always positive. All right? So if the bottom is always positive, then this fraction is positive if and only if the top is positive. Everybody understand that logic? The whole fraction would be positive if the top and bottom are both positive, or the top and bottom are both negative. Since the bottom is always positive, the only way for the whole fraction to be positive is if the top is positive. Since the top is just x, this fraction is positive if and only if x is positive. And that's precisely because x squared plus 9 is always positive. Why is x squared plus 9 always positive?
Any number squared is positive.
Yeah, good. The square, x squared, is always greater than or equal to 0. You add 9 to something that's non-negative, you get something strictly positive. All right. So positivity is satisfied. Is this function continuous? Well, f of x equals x over x squared plus 9 is a rational function. Remember what rational function means? It means it's a ratio fraction made up of polynomials. The top and bottom here are both polynomials. Therefore, it is continuous everywhere except where the bottom is equal to 0. But the bottom equals 0 means x squared plus 9 equals 0, which has no solutions, no real solutions. Because x squared plus 9 is a irreducible quadratic, right? Remember that term irreducible from back in section 7.4? That's useful here as well. X squared plus 9 is irreducible, meaning it doesn't factor, which means there are no real roots. So there are no real numbers which make the bottom 0, which means this thing is always continuous. I'd say therefore. And I'm leaning on a theorem, right? I'm leaning on that theorem from 2.5 that we discussed in class earlier. Theorem 5 from section 2.5, a rational function is continuous wherever it is defined. That is continuous on its domain. So this is a rational function, and its domain is all real numbers because the bottom is never 0. So it's continuous everywhere. F of x is continuous everywhere.
If the bottom here had asymptotes where it was like not where it was outside of the original domain, would that be an issue, or would we just call it like good?
No, that would be fine. If the bottom was equal to 0 when x was like -2 or when x was 0, that would be okay because the interval in question here is 1 to infinity. So I'm going to say specifically on 1 to infinity. Yeah, the interval in question here is the interval from 1 to infinity because that's where we're summing from. That's where we'll be integrating. So 1 to infinity. As long as we don't have any discontinuities there, we would be happy. You can have a discontinuity somewhere else. If you got a discontinuity at 0 or -5 or 1/2 or 0.7, that would be fine too. And then finally, decreasing. This is where all the work is, right? And here, we're going to have to do some work. I can tell you what the graph looks like. It's called a witch. It's kind of like a thing like this. So there's a non-trivial amount of work here. It's not always decreasing. The gain, because it's certainly not the reciprocal of an increasing function, is to take the derivative. F primed is d dx of x over x squared plus 9. And this is one of those rare cases where I actually endorse use of the quotient rule. I think this is an appropriate problem to use the quotient rule on. If we do that, we have the bottom times the derivative of the top, which is x squared plus 9 times 1 minus the top times the derivative of the bottom, x times 2x, all divided by x squared plus 9 quantity squared. So upstairs here I have x squared plus 9 minus 2x squared. That's going to simplify to 9 minus x squared over x squared times x squared plus 9 quantity squared. Is everybody with me on this? Take a second, verify the algebra. So what do I want to do with this? It's not always negative, right?
Find out when it's 0, and then make a sign chart for the left and right of each 0.
Very good. So I need to figure out where this thing, which is f primed, is positive and where it is negative. Hopefully, it will be negative on some interval extending off to infinity. And in order to do that, we're going to make, like Alexander called it, a sign chart, like a number line. In order to do that, we need to find the critical numbers. Critical numbers are places where this thing's capable of changing sign. And there's only 2 of those such things. It's going to be plus and minus 3. So the critical numbers.
What would you have called it? That's just what I've always called it from like
Sign
school.
chart is fine. I think when I teach, I call it a number line. That's all. It's the same idea. So you're going to build a number line and figure out the regions where this thing is positive and negative. So my critical numbers come from places where f primed is 0 or undefined.
Plus and minus 3.
Yeah, f primed will be 0 when x is plus and minus 3. That's coming from setting the top equal to 0.
And the bottom is never 0, so nothing comes from that.
Good, yeah, so we're never undefined. So the only things I need to worry about here are -3 and +3. And this is a number line for f primed. I'm going to figure out where f primed is positive and where it is negative. Between -3 and 3, we can test 0. F primed of 0 is 9 minus 0 over 0 plus 9 squared. That's 9 over 81, or 1/9, which is positive. So this function is increasing from -3 to 3. F primed of 4, over here to the right of 3, I test a point, is 9 minus 16, which is -5, divided by 16 plus 9 all squared. I don't know if I know what that is. Oh, wait, actually, I've got web it up, don't I? It's better. $625. But in particular, it's negative. And this is all I need. I don't actually care about what's happening over there. So,
Sorry, can I ask a question?
sure.
So this is where I keep getting stumped. Does it not have to be negative for the whole interval in order to pass the criteria for the integral test?
Correct. And that's what we talked about at the beginning of class today, if you recall. We said we can relax those conditions a little bit. Let me see if I can find it. Here we are. So as long as we're decreasing on some interval of the form c to infinity, where c is greater than or equal to the number where your series starts. So it's true that this thing is not decreasing right away. But as long as x is greater than 3, this thing will be decreasing. So that was one of the things, one of the like subtle things that we talked about earlier today. Basically, what we're doing is we're saying, okay, instead of applying the integral test to this series, I'm really thinking of it like I'm applying the integral test to the series starting at 3. Those 2 series only differ by 2 terms. So if the one starting at 3 converges, the one starting at 1 will converge. That's kind of the logic there. But the simplest way to think about it is that you can relax the requirement from decreasing everywhere on that interval to decreasing eventually. Does that make sense?
Yes, thank you, Professor.
Sure, of course. I agree that this can be a little bit confounding at first, especially because the theorem is stated one way, and then we apply it so often to things that don't exactly suit that. But yeah, this is good. So we'll say f prime is negative for all x greater than 3, which means f of x is decreasing for all x greater than 3, which is good enough for us. And then the last bit here, we would need to compute the integral. So the, let's say now, integral 1 to infinity x over x squared plus 9. Since we've come this far, we might as well finish the problem. How do we do this integral?
U sub with x squared plus 9 equaling u, and then du equals 2x.
You're correct, but what should I do before the u sub?
It's improper, so you have to do the limit as r approaches infinity of 1 to r.
Very good. Don't forget this step. It's a finicky step, but it's something that I do have to take points off for when I see it not done. So please be mindful of that. Because technically I cannot do u sub on this integral here because it isn't a Riemann integral. You know, it might seem silly, but I promise it's important. And then the u sub is just as Alexander said for x squared plus 9. Du is 2x dx. My bounds will change. 1 goes to 10. And r goes to r squared. All right, u equals r squared plus 9. And what I get out of that is the limit as r goes to positive infinity, integral of 10 to r squared plus 9. There's a 1/2, and then I have 1 over u du. And that will be a natural log. So lim r to infinity, 1/2 natural log absolute value of u evaluated from 10 to r squared plus 9. Which will be lim r to infinity, 1/2 natural log absolute value of r squared plus 9 minus the natural log of 10. What does this limit do?
Natural log of r squared plus 9 goes to infinity.
Good, because as r gets bigger and bigger, r squared plus 9 gets bigger and bigger.
So it diverges.
And as we saw in class earlier today, as the inside of the natural log gets bigger and bigger, the whole thing goes to infinity. So we would say that this is 1/2 times infinity minus the natural log of 10, which is infinity. So the integral diverges.
Which means the series diverges.
Good.
Now I want to clarify, did we say that even if the integral converges, that the series does as well?
Yes.
Okay.
Yeah, that's the idea, is that under those conditions, the integral and series do the same thing. So if the integral converges, the series converges, and if the integral diverges, the series diverges.
So the only one that's going to leave us maybe with a with us being unsure is the test for obvious divergence. Is that correct?
Let me make sure I understand the question right. So you're asking like the only place where we have an inconclusive result, right?
That's what I'm trying to ask. Yeah.
Yeah, so far, the only one like that is TFOD, but there will be others.
It's frustrating that we can't actually find the values that these converge to. It's really
Incredibly
frustrating.
frustrating. Incredibly frustrating. I actually have a, see, while I've got you thinking about that, does anybody know the value of the P series with P equals to 2? So Alexander made a comment. It's frustrating that we can't find the value of these sums. It's incredibly frustrating. This one is known. So what I'm getting at here is that many of these are just not known. I don't mean like I can't teach you how to do it. I mean like no one can teach you how to do it because no human being knows. But this one is an exception. Is anybody familiar with this guy?
This isn't the pi squared over 6 thing, is it?
Yes, yes it is. This is pi squared over 6, aka zeta of 2, where zeta here, zeta of s, is the Riemann zeta function. You actually have a homework problem about this. Proving that zeta of 2 is pi squared over 6 is quite tricky, but it's not unmanageable. It involves working out an infinite series for and an infinite product for the sine function. It's called the Basel problem, if you're curious about this. So the proof of this was first done by Euler. The same Euler after whom we name the number E. And it's called the Basel, after the town in Switzerland, Basel problem. And the solution, Euler's solution to the Basel problem, is one of those really beautiful things. One of the first things I saw that made me fall deeply in love with mathematics. It's fascinating if you want to see it. Zeta of 4 is also known. This is pi to the 4 over 90. And in general, the sum from 1 to infinity, 1 over n to the 2k, which is zeta of 2k, there are formulas for this. The formulas involve Bernoulli numbers. You remember when we talked about L'Hopital's rule, we mentioned the Bernoulli brothers. One of the Bernoulli brothers famously devised a sequence. That sequence is called the Bernoulli numbers. The formula for these things are given in terms of powers of pi and the Bernoulli numbers. Strangely though, this one is still unknown. A mathematician named Richard Askey. No,
Why is that name familiar?
Not Askey, Aperi proved this number to be irrational. Richard Askey is a pretty well-known guy among mathematicians in town here if you live in Gainesville, because he's done some work with the Ramanujan journal, Askey-Wilson polynomials, orthogonal polynomials, hypergeometric series, which like in the Gainesville math circle is very important because Krishna Alati is the editor of the Ramanujan journal. And Richard Askey is a very well-known figure in that little subworld of mathematics. But Aperi, I think there's an accent over the E here, I forget. This number is called Aperi's constant. It's definitely a convergent series, right? So it has a value, but we don't know exactly what it is. There are tricks for evaluating it. You can just write out a big ass partial sum and it'll give you something close. But the actual value is not known. But Aperi relatively recently, proved that it was irrational.
Can we say that the value of any irrational number is known?
Oh yeah, I mean, sure, yeah, E, pi, we know those numbers.
We don't know every digit. We can't know every digit, so we just know approximations, right? Like, what's different about this?
Well, pi is the ratio of a diameter to a circumference. Like it depends on what you mean by known. Do I know every digit in the decimal expansion of pi? No. But do I know what pi is? Yeah. In the sense that we don't even know, we don't know this as well as we know what pi is, that's what we mean by unknown. Like there is no expression for this number in a finite amount of terms as a function of known constants. That's the idea. You're getting into kind of like ontological and metaphysical questions there, which are fun. Yeah, I would say this is unknown in the same sense that like, say it, in the same sense that like mysteries about which we have no information are unknown.
But just by brute forcing calculating, say, 1 trillion terms, like we could get a really good idea of it. Yeah.
Sure, yeah, and it's been calculated out to many, many decimal places. And there's a lot of representations for it. But you know, so here's like the first whatever dozen, 2 dozen digits. But that doesn't mean we know exactly what it is. Anyway, let's continue moving on in the constructive direction with other problems we wanted to look at. I think there was one in chat that we haven't gotten to just yet, right?
Yeah, homework number 29.
Yeah, okay. Whoa, no, kitty, get down. I love you, kitty. You gotta move though.
Aww.
She's a cutie. She likes to hop up on the desk while we're trying to work. We wanted 29.
Yeah, that's correct.
Oh yeah, this is excellent. All right. So I would like you guys to kind of talk me through this a little bit. This is about the caliber of question that you can expect on the exam when it comes to questions about geometric series. Hint nudge. What do we do here?
My brain's pretty fried right now, but I'm guessing that the thing wrong with this is that the result of the equation, since it's kind of like oscillating, relies on which term you're going to. So if you go 1 step forward, it goes to 0, and if you go 1 step after that, it goes to 1.
Oh, sorry, that's correct for number 30. Yes, very good answer for number 30. The partial sums here oscillate between 0 and 1, which means that the sequence of partial sums is not a convergent sequence. Therefore, this is a divergent series. And these sort of computations are not kosher with divergent series. However, number 29 was the one that was asked about, right? So how do we handle this?
Well, this is geometric, yeah. It's going to be 1 over 1 plus c to the n.
Good. So I would begin by saying sigma n from 2 to infinity, 1 plus c to the negative n is the same as sigma n from 2 to infinity, 1 over 1 plus c to the positive n.
Which equals 1.
Let me put that over here. Because what I want to do is I want to evaluate this as an infinite series. And that will give me an expression that doesn't have a sigma in it, right? If I can use what I know about geometric series to get a nice formula for this, then I'll set that equal to 1 and solve for c. That's the long game here.
And we know that c has to be greater than 0, right?
Yeah, let's come up here just for a second. This is a geometric series with r equal to 1 over 1 plus c. So it only converges if the absolute value of r is less than 1, i.e. the absolute value of 1 over 1 plus c is less than 1. Now there's a handful of ways you can attack this inequality. You could start by taking reciprocals on both sides, and that would flip the inequality over. So I'd get absolute value of 1 plus c is greater than 1. And then we can say that this is equivalent to saying 1 plus c is bigger than 1, or 1 plus c is more negative than -1. And then if you clean each of those little inequalities up, here you get c is greater than 0, or c is less than -2. So in order for this series to converge, we need one of these things to be true. In other words, if you were to solve your equation at the end and get a c value that doesn't satisfy one of these, you have to kick that guy out. All right.
So then we can use the first term over the 1 minus the common ratio formula and
Right.
solve that for 1, or in my case 3.
So if we assume the series converges, then this should be equal to, just like Alexander said there, the first term over 1 minus the common ratio, because it's a geometric series. That's how those work. What's the first term of this series? What?
1 over 1 plus c squared.
Very good. Because the series begins with n equal to 2, our first term is 1 over 1 plus c squared. Come on, pen. Like this. And our common ratio is 1 over 1 plus c. Like this. So at the end of the day, this is the thing that we need to set equal to 1 and solve. And it's a somewhat complicated looking rational equation, but we can clean it up pretty significantly by multiplying top and bottom by 1 plus c. There's a bunch of ways to do this. So we need to solve 1 equals, I might switch colors here, I hope you forgive me. 1 equals 1 over 1 plus c quantity squared over 1 minus 1 over 1 plus c. There's a bunch of techniques for solving equations like this, which hopefully you're familiar with. I would probably start by saying this is equivalent to 1 equals 1 over 1 plus c squared, right? Because 1 squared is 1, minus 1 over 1 plus c, like this. And then we can multiply top and bottom by 1 plus c. And remember, we need to think of the tops and bottoms of all fractions as being in parentheses. So that is equivalent to saying 1 equals 1 over 1 plus c, that this will cancel one of those, divided by, when I distribute this here and here, I'll get 1 plus c minus 1. This. There's other ways to do this too, but I think this is the fastest. This is equivalent to saying 1 equals, remember top and bottom always in parentheses kind of, 1 over 1 plus c divided by 1 plus c minus 1 is just c.
And then here, just multiply by 1 plus c again on top and bottom.
You could, or you could multiply both sides by c to bring the c over to the left-hand side. There's lots and lots and lots of options. I would probably do the latter and say here now c is equal to 1 over 1 plus c. And then again, multiply both sides by 1 plus c. Or I guess we haven't done that yet. We can multiply both sides now by 1 plus c. We get c times 1 plus c equals 1. So in other
So
words,
c squared plus c plus 1 equals 0, or minus 1 equals 0.
minus 1. Yeah, very good. And then we can take that over here and solve that quadratic. So I don't know if this factors nicely. It doesn't look like it will, right? Two numbers who multiply to -1 and sum to +1. I don't think those exist. Not integers, at least. Yeah, no, they're not, certainly not obvious. So you could use your quadratic formula from here. You can complete the square. Let's just use the quadratic formula. So c is equal to -b plus or minus the square root of, I shouldn't call them a, b, and c, but your quadratic formula will do the job here. So b squared minus 4 times 1 times -1. Yeah, this is going to involve the golden ratio, I believe. Over 2. So that's -1 plus or minus the square root of 1 minus 4 times -1. That's the square root of 5 over 2. So c is either -1 plus root 5 over 2, or c is equal to -1 minus root 5 over 2. And we'll need to check whether these live in this territory or not. I believe this one will. Sorry, this one. This one is positive because root 5 is bigger than 2. So this is certainly possible. This guy is going to be negative, but is it more negative than -2? I don't think so. So root 5, let's just pretend like that's a little bit bigger than root 4, which it is. Then that would be 2. So this would be -1 minus 2 is -3 over 2 is not less than -2. So I think this one is greater than 0. So he's good. This guy is negative, but not less than -2. So we got to throw him out. So this one, which is sort of like the golden ratio, is our solution here. Now the algebra at the end is a little bit complicated. This isn't something that I would necessarily want you to burn time on a test, but the concept here is really cool. So saying, here's a geometric series with an extra little parameter in it. I want you to tell me for what values of that parameter does the series converge, and then figure out the sum of the series and solve an equation. This is a very good problem, and problems like this do have a way of showing up on exam too. Is there any part of this we'd like to look at more carefully?
Yeah, there's a problem that I had. Hold on, let me pull it up. 13 on homework 9.
I'm sorry, before I move on from this problem, are there any other questions or anything we want to look at more carefully with this problem? I'll be happy to do that one next. Anybody else?
Not that I could think of.
Okay, so Ethan, you were saying homework 9, number 13? All right. This is good. So the particular integral test problem I started class with today, I chose that specifically so that you could use that to help you solve this problem. I don't want to spoil the whole thing for you, but I'll tell you it is the integral test. And I can show you how to get started. Let me say, yeah, okay. It's the integral test. F of x here is 1 over x times the natural log of x all raised to the p. The continuity, positivity, and decreasing arguments are identical to the first problem we did in class today. We're continuous aside from x equals 0 and x equals 1. We're positive as long as x is greater than 1, because that's where the natural log shifts to being positive. Depending on this power, that may not even matter. And we're decreasing because x times the natural log of x all to the p is increasing. And I'm going to eschew those details here. But you might want to think a little bit about why that's the case. You might want to look back at the first problem that we did in class to make the argument about those details. Specifically, this last guy is a little bit subtle, but I would say x is increasing. And the natural log of x all to the p has derivative p times the natural log of x to the p minus first times 1 over x. And this is positive for all x greater than 1 independent of p. So if p was odd, then p minus 1 would be even, and this thing would always be positive. So this would be the only term to care about, and this term is positive as long as x is positive. If p were even, then p minus 1 would be odd, and this term would take the sign of the natural log of x, which is positive as long as x is bigger than 1. So independent of the value of p, as long as x is bigger than 1, this is positive. Since this is the derivative of the bottom, that means that the bottom is increasing. It's the derivative of part of the bottom. So x times the natural log of x to the p is increasing, which implies f of x, which is its reciprocal, is decreasing. And then the good stuff here is the integral from 2 to infinity 1 over x times the natural log of x to the p dx. This is actually hearkening back to a 7.8 problem. Remember, way back in section 7.8, you guys determined the values of p for which this integral converges. This was a problem you had there. The way you do it is by first writing as a limit subbing for the natural log. Change your bounds. And then in a kind of clever roundabout fashion, you transform this into a p integral. So this becomes 1 over u to the p du. And then you can say as r goes to infinity, the natural log of r goes to infinity. We can rewrite this as an improper integral. Which is a p integral. Therefore, this integral converges if p is bigger than 1 and diverges if p is less than or equal to 1. Hence, by the integral test, the series S converges if p is bigger than 1 and diverges if p is less than or equal to 1. So this is a cool problem. And it's not super straightforward, but it should kind of, I want you to work through this and take your time. So it's very much worthwhile for you to start making these connections. This integral should look familiar, right? This is one that we talked about, and this very clever trick of like doing the u sub to get to here and then rewriting it again as an improper integral. It's a very slick move. If you don't see that you can do that, then you can go ahead and compute an antiderivative for 1 over u to the p, but you're going to have to take separate cases. You're going to have to consider the case where p is 1, separate from the case where p is not 1. And then the cases where p is not 1, you're going to have to break those into whether p is greater than 1 or less than 1. And it gets quite complicated. So having seen this once before, when we talked about it in section 7.8, I would hope that you could construct this argument on your own here. So I think it's worthwhile to kind of give yourself a little bit of time to forget, come back and try to attack it. And if you get stuck, then come back and look at these notes or rewatch this video. All right, I expect that we're approaching the threshold of patience here. Are there any other problems that you guys are dying to look at right now?
I have one.
What's up?
On the latest homework, number 4.
All right, we'll take a look at this and then we'll wrap it up. No.
It's just finding the p-value that I'm having issues with. Not much. I mean, I know it's convergent.
Yeah, this is, well, who can help us with this? The trick is to first write this in sigma notation.
I know that, but I just couldn't find the sigma notation, the proper one, the proper ratio.
So don't confuse geometric series with p series. They are different animals. There is no common ratio here. So this is 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. What do you notice about those denominators?
Oh, I realize it now. Yeah, it's just n.
Well, kind of. So
It's just the p is equal to 2. I should have realized that. I'm sorry.
no, don't be sorry. Don't be sorry. I think this
I
is
confused it with geometric. I'm sorry.
Please don't be sorry, especially for folks who haven't solved this yet. Take a look at these denominators. What do we notice? They're all perfect squares, right? 1, 4, 9, 16, 25 would be the next one. So this is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. So in sigma notation, this would be sigma n from 1 to infinity, 1 over n squared. And it is a p-series with p equal to 2. And since that's bigger than 1, the series converges. All right. So I do think this is a reasonable place for us to leave things off for today. If you have not finished the spring break homework, please start sinking time into that immediately. Like, the best time to do it is right now. One of my favorite figures of speech, there's only one moment when shit ever gets done, and it's now. If you say, I'm going to do it later, I'm going to do it later, there is no later. Now is the moment when shit gets done. So if you haven't finished that, start it right now. If you get stuck on anything, please ask questions. I've granted all the extension requests that were in. I'll go through and look and see if there are any others. But if you haven't done that, you need to do it. You need to do it now. As soon as you finish that, move on to this week's homework. This material is challenging, and you need to be sinking the time in order for it to go okay. I'm happy to spend all the time in the world with you to help, but you got to be willing to invest the time too. So please make sure you're investing the appropriate amount of time. This is the hardest part of the hardest class in the whole calculus sequence. So invest the time and treat it with respect, and you'll be all right. If you don't, there's not much we can do. It's going to go badly. So please sink the time in now. Get comfy with this notation, right? This notation scares the shit out of a lot of people. And that's understandable because it's new notation. It's not something that you've seen much in Calc 1 or in pre-calc. So spend the time, understand it, ask the questions, and use the Discord. Talk to your peers. If you have a solution you're not sure about, or you're really proud of, or you want to argue, it's just fun to like sit around and argue about this shit. Please do that. It will benefit you hugely. If you want to talk, I'm here. Otherwise, I will see you guys next Tuesday, okay?
All right. Have a great day, Professor. See you later.
You too, guys. Take care.